Good evening to all. Am I audible? Am I audible? You can just message in the chat box. Just type in the chat box yes or no. Okay, just type yes. Okay. Okay, I will upload the attendance sheet at the end of this session. Okay, I will just give you the link. You people can fill that form. Okay, so it's just it's like a feedback, a Google form. That's it. Nothing is there. Very few questions. 1 or 2 questions will be there. You just fill that later on. I'll just start the class. Okay, today we will discuss about differential relays. Today we'll discuss about differential relays. I'll చెప్పండి దయచేసి ఉంటుంది. I will start the session. If the number of concurrent viewers decrease, I will stop the session because it's wastage of time if sufficient people are not attending the class. Okay, it's your wish. No? I'm not going to gain or lose anything. If I just conclude the session, if sufficient viewers are not there, I will just conclude the session. So let us see what is meant by differential relays. So the differential relays, they are the protective relays. We can even call them as differential protective relays. They are more sensitive than any other overcurrent relays because these can distinguish between heavy loads and minor fault conditions. So these relays, differential relays, they are very much more sensitive when compared to the overcurrent relays because they can easily distinguish between. They are very sensitive when compared to overcurrent relays. They can easily distinguish between heavy load means heavy fault. Heavy load means heavy fault condition and minor fault condition. Okay. So these differential relays usually they will have 2 or more similar electrical quantities. Okay, and these similar electrical quantities should always have a phase displacement. Okay. So these differential relays which are used for protecting the power system equipments, these should always have 2 or more similar electrical quantities, and these quantities should have a phase displacement. So usually the phase displacement will be approximately 180 degrees. The phase displacement between the similar electrical quantities will be around electrical quantities means usually current or voltage. Okay, so they will have a phase displacement of around 180 degrees for the operation of this relay. And the differential relay is defined as the relay which is, you can see here, is written here. It is defined as the relay that operates when the phasor difference of two or more similar electrical quantities exceeds a predetermined amount or predetermined value. So when the phase difference between two similar electrical quantities, two or more similar electrical quantities exceeds certain predetermined value, then only this relay will operate. Okay. So when I show you the diagram and when I explain it along with the diagram, it will be more easy for you people to understand. Okay. So at present, I'm just giving the introduction to this differential relay. So here I have been telling that there will be two or more similar electrical quantities. Okay. Uh, who, these two electrical quantities should have a phase difference for the relay to operate. So the difference between these two electrical quantities can operate this relay to isolate the faulty section from the healthy section. Means if fault occurs in one section of your power system, that section is to be isolated from the remaining healthy section of the power system. So this differential relay will disconnect the unhealthy section from the healthy section. And we can use any type of relay till now, whatever relays that we have discussed. Among those relays, you can use those relays and you can operate them as a differential relay. Okay. So any type of relay can operate as a differential relay simply by casting two similar electrical quantities which has the phase displacement. Okay. So most of the differential relays are current differential relays. Okay. Most of the differential relays in the power system are current differential relays. So this type of current differential relays will have a phase difference between the currents entering the winding and current leaving the winding. Okay. So if differential relay is current differential relay, then here electrical quantity that is used uh, to operate this differential relay is current. Okay. So current differential relay means current is the operating value. So there will be comparison between the entering current as well as leaving current to this differential relay. So the current entering this differential relay, if its phase is means if it has a phase displacement of so and so value with respect to the current leaving this differential relay, then and if it exceeds the predetermined value, then this relay will operate. Okay. So the protected zone is exactly determined by the location of the CTs and P2s. So this relay, this differential relay will always have the current transformers or potential transformers which will decide the boundaries of the operation of this relay. So differential relay, its operating boundaries from which location to which location this differential relay will operate will always be decided by the location of the current transformers and potential transformers. So there will be current transformer at the means at the beginning of the location from where this relay has to protect until the end of the section where this relay has to protect. So the zone which has to be protected by this differential relay, that zone starts with a CT, ends with a CT, or that zone starts with a PT or ends with the. Okay. So the boundaries of this differential protection relay are all set by this CTs or PTs. So I just want to check whether you are able to follow or not. You just text someone, send a text message mentioning that you are able to means there whatever text is there, the text and the audio both are matching. Whatever I'm displaying on the screen and whatever I'm speaking, both are matching with each other. If there is any disturbance or if my voice is not audible, you just mention in the chat box. is the screen that is displayed along, as well as the voice that my voice, is it syncing with the displayed screen or not? No disturbance. Okay, then I will continue. Okay, so till now what we have discussed is that the differential relay, its protected zone, from which location to which location, this from one location to the another location is the protected zone of this relay. So that location boundaries are decided by the location of the potential transformers and current transformers. Okay, so the phase difference of the electrical quantity is achieved by suitable connection of the secondaries of the CTs and VTs. And this differential protection principle is employed for the protection of generators, generator transformer units, transformers, or tweeters, or large motors or bus bars. So the differential protection can be used for either protection of generators, generator transformer unit, or transformers itself, or the feeders, that is transmission lines, or large motors and bus bars. So there are different types of differential relays. Let us see those differential relays. Types of differential relays are current differential relay, biased or percentage differential relay, and voltage balanced differential relay. So let us discuss these differential relays one by one. The first one is current differential relay. After that, we will discuss percentage biased. Here it is mentioned biased or percentage differential relay on this screen, but you can even call it as percentage biased differential relay. Next, voltage balanced differential relay. Okay, so let us start with the current differential relay. So you can see this protected system element, it is mentioned, this dotted line portion is mentioned as protected system element. So this can be a winding of a transformer or a generator, okay, or a transmission line or a bus bar, okay, any portion of the equipment which is to be protected. Let us assume this is the portion of some element which is to be protected. So since I want to protect this element, okay, let us assume it is the winding of a transformer, let us assume. So here winding of the transformer is there. I want to protect it against the fault. So on either side of this winding, I will connect CTs. Here one CT is there, here one CT is there. So CTs are connected. So as I have already told you just now earlier, that CTs will decide the boundaries of protection. So CT1 and CT2, they are deciding the boundaries of protection. So if fault occurs within this zone, then relay will operate. Okay. So let us assume, let us give some notation to this CT, that is CT1. Let us give some notation to this CT, this is the CT2. Okay. So if you observe the secondaries of these CTs, they are connected. Secondaries of these CTs are connected, and across the secondaries of these two CTs, a relay coil is connected. We know what is meant by relay coil, isn't it? This is the relay coil, which is connected across the secondaries of both the CTs. Okay. So the wires that are used to connect the secondaries of the CTs, they are known as pilot wires. Okay. Pilot wires are used to connect the secondaries of the CTs. Okay. So this relay coil, that's what I have told you. It can be an overcurrent operating relay. Okay. So the relay coil which is used here, it can be an overcurrent relay. So overcurrent relay can be used for differential protection, we can say. Okay. Now let us assume that here, let us assume, where is my cursor? Yeah, this is it. So let us assume this is our till now what I have discussed is that this is our protected zone, isn't it? Now let us assume fault has occurred outside the protected zone. Okay, so this is the fault. Okay, fault has occurred outside the protected zone. Okay, or in other words, I can say that no fault has occurred within the protected zone. Okay, either fault has occurred outside the protected zone or no fault has occurred within the protected zone. Then the currents entering both the CTs, okay, two CT secondaries are equal and relay operating coil does not carry any current. That means that now let us, here you can see current I is entering this CT. Okay, so when current flows to the this CT senses the current in this line, it will produce what? What will happen across its secondary? Some EMF is induced. Corresponding to that EMF, some current will flow. Some I amperes of current will flow. Okay, the same current will flow through this CT also. Corresponding to that, some EMF is induced across its secondary. My cursor is very sensitive. So if I press a bit harder, then what will happen is straight lines will appear. I have to be okay. EMF. These are this. See, this is what happens. I have this issue, but I won't change my cursor. Even though I have an issue with my cursor, I won't change the cursor. Sorry, I won't change my mouse. Huh? Okay, it's the issue with my mouse. It's very sensitive. Okay, so the current entering CT1 and CT2 is same. So EMFs induced across the secondaries will also be same. So whatever current, you can see here this relay coil or the overcurrent relay is connected across the secondaries of both the CTs. So whatever current that is entering this junction, same current will leave this junction. Okay, same current will leave this junction. So there is no difference in these two currents. Means the currents that are flowing in the secondaries of these two CTs in the pilot wires, you can say. Okay, in the pilot wires will be same current. So there is no difference in this current leaving the. This is our junction. Okay, I will once again do. Okay, this is our junction where the relay coil is there. Okay, or overcurrent relay is there. Now the current entering this junction and the current leaving this junction will be same. Okay, so usually in our circuits, what we have learned is that if there is a junction, current should divide. But here this is not a connecting wire or anything else. It's an operating relay. Okay, so in this relay, current can flow only when there is difference between the entering current and leaving current. Okay, so this is our entering current. This is entering current. And this is leaving current. Okay, just simply I have written E and L. So entering current and leaving current magnitude simply, okay, simply magnitude should be if they are same, not should be, if they are same, then no current will flow. I lost my cursor here. No current will flow through this relay. So the current entering this relay is 0 amperes. Current entering this relay coil or the overcurrent relay is 0 amperes. The current that is entering this junction and leaving the junction both are same. So the differential current will not, there will not be any differential current. So no current will flow through the relay coil. So don't think that it's not the similar concept of our circuits. If there is a junction, current should divide it. This is not a junction here. It is an operating relay that is connected here. Okay, so there should be difference between the entering current and the leaving current. Then only the differential current will flow through the relay coil and the relay will operate. So when the entering current and leaving current are same, why entering and leaving current at this junction are same? Why? Because the EMFs induced have this issue always. I forgot about my mouse and I just pressed harder. And the EMFs induced across the secondaries of this CTs is same. Why? The EMF induced across the secondaries is same. Why? Because the current entering this CT and the current, or we can say, or the current leaving this CT2 Current entering CT1 and current leaving CT2 are same. Okay, so no current will flow through the relay coil, hence this relay will not operate. So under external fault condition, external means beyond the protected zone, if fault occurs, okay, or if no fault occurs within the protected zone, this relay will never operate. Okay, this relay will never operate. Now let us consider the opposite case. Okay, opposite case is what? Where is my another diagram? Oh no, only one diagram. One more diagram should be there. Yeah, this is another diagram. So another case is what? Fault has occurred within the protected zone. You see in this image, where is my cursor? Yeah, in this image, internal fault. It is mentioned internal fault here. So fault has occurred within the protected zone. Okay. So now, if fault occurs, we know fault current can flow in either any direction. Okay, so because of the fault, current can enter from both the direction. We already know that current should always should come out from the generating station and travel towards this distribution station, isn't it? But if fault occurs, current's directions may change. Okay, so current can enter from both the directions. Okay, or current direction may not change. If this side generating station is there, current is entering the city and current is still leaving the city, means current direction has not changed in this diagram. Okay, current direction has not changed, but fault has occurred. Some internal fault has occurred. So what will happen? The current entering CT1 will no longer be equal to the current leaving CT2. So if you carefully observe in this image, it is mentioned here I1 and I2. That means the current entering CT1 is no longer equal to the current leaving CT2. So EMF induced across CT1, it might be E1. EMF induced across CT2, across the secondaries of CT2 is E2. So current flowing through the pilot wires because of this induced EMF across the secondaries of CT1 is I1. Current flowing through the pilot wire due to the EMF induced across the secondary of CT2 is I2. So I1 and I2 are not equal, so the difference of these two currents will flow through the operating coil, and if that difference exceeds the preset value, predetermined value, see, always the fault should exceed the predetermined value. Okay, so there will be some preset value already in the relay. Okay, and relay always compare the measured value with the already preset value. So if it exceeds the predetermined value, then relay will operate, otherwise relay will not operate. Okay, so if internal fault occurs, the EMFs induced across the secondaries of CT1 and CT2 will no longer be same. Okay, and the currents flowing through the pilot wires, of these two CTs. Okay, the pilot wires mean these are the pilot wires. This wire, this wire, this wire, and this wire. The current will no longer be same. So the differential currents, the difference of these two currents will flow through the operating coil, and if it exceeds the preset value, then relay will operate. Okay, so I am talking in terms of magnitude here, but earlier I told you that these two currents will have a phase difference. Okay, so here I didn't mention anything about phase difference, but this differential relay will, the differential relay, which means the operating relay coil or operating relay, overcurrent relay, which I have used here, the current flowing through this, okay, the current will be proportional to the phase difference between these two currents. Okay, the current that is flowing, the differential current, I1 difference, I1 minus I2 or I2 minus I1, whatever, the differential current will be proportional to the phase difference between the currents entering and currents leaving the protected element. If the differential current exceeds the pickup value, that is preset value, then the relay will operate, otherwise relay will not operate. Okay, so I hope you have understood. If you are listening carefully, you might have been able to follow what I have been trying to tell you. So remember one thing, that differential current has to flow through the relay coil. So when differential current will flow through the relay coil, whenever the current entering CT1 and current entering CT2 is different because of the internal fault. And if it exceeds the preset value, then only relay will operate. So there are some difficulties that are associated. So I think some theoretical content I have kept on the screen, but I didn't show you. It's okay. So there are some difficulties which are associated with this differential protection. Those difficulties are difference in the length of the pilot wires. So the pilot wires which are connected between the secondaries of the CTs, their length should be same. Their length should be equal. Okay. So the length of these pilot wires should be equal. If the length is not equal, then same current may not flow through the pilot wires. Okay. So usually the power system elements which are to be protected, okay, and CTs, they are not located in the same places, isn't it? They are located at different places. Okay, and normally it is not possible to connect the relay operating coil to the equipotential point. Okay, so the relay should be connected at the equipotential point. So this point you can call it as equipotential point. So relay should be always connected at the equipotential point, then only equal amount of EMS will be induced across the secondaries when same current is flowing. Okay, so it's better I will show you another this time. Okay, and same current will flow through the secondaries of the CTs if the relay coil is connected at the equipotential point. If it is not connected at the equipotential point, then there will be difference in the lengths of the pilot wires. Okay, next difficulty is, where is it? Next difficulty is CT ratio error during the short circuits. Okay, CTs used may have almost equal ratio at normal currents. When normal current is flowing, then the CTs will have equal ratio. But during fault condition, what will happen is the primary currents are unduly large and ratio error of CTs on either side will differ. Okay, the ratio error will differ. So that is one of the drawback. Okay, and one more difficulty here is saturation of the magnetic circuits of CTs under short circuit condition. Okay, so when current flows through the CT, what will happen? Magnetic flux will be induced. Okay, so after if fault occurs and if the current is gradually building up, okay, after reaching certain value of current, what will happen is the flux will not, even the fault is increasing, the flux that is induced in the CTs may not increase. Okay, it may get saturated under faulty condition. So the differential relays of this type are likely to operate inaccurately with heavy faults. Okay, if fault is very severe and if CTs become saturated, mean the flux density is not further increasing, okay, then the operation of this relay will not be accurate. This type of relay in which CT's magnetic circuit is being saturated. Okay, so this drawback, this saturation drawback, it is overcome by using another type of differential relay, which is known as percentage biased differential relay, or percentage differential relay, or biased differential relay. So this saturation of magnetic circuit drawback, it can be overcome by using biased differential relay. Next, one more difficulty is which is associated with the differential protection is the magnetizing current inrush at switching instant. Okay, when we usually know under no load condition, the current flowing through any equipment, usually if there are coils, then magnetizing currents will be there. So if under unloaded condition, if we want to protect a transformer Okay, if we want to protect the transformer and if no load is connected across its secondaries, then magnetizing currents will flow into it. Okay, and since what will happen is because of the inrush, okay, of these currents, the relay may not unnecessarily relay may operate because of the inrush of these magnetizing currents. Okay, and next drawback is tap changing. Okay, tap change means if there are transformers, transformer transformation ratio is changed whenever taps are changed. Okay, if there are transformers, their transformation ratio is changed whenever taps are changed. Due to this, CT ratios do not match with the new tap settings. Okay, so if tap setting is provided to the transformer windings, then the CT ratio may not match with the new tap setting, and it will result in flow of current in the pilot wires, and the differential current may unnecessarily operate the differential relay. So, in order to overcome this problem, also percentage bias differential relays are used. Okay. So let us see this percentage bias differential relay. So am I in the class? Can anyone? Am I in the class? Can anyone mention? Am I in the class? Percentage bias differential relay. Next, just now I have to start it, but I just wanted to make sure that I'm still in the class. Okay, so I'm just checking in between because I'm just coming out of the class to deliver the lecture. I'm just looking at my presentation. That's it. So, okay, I will continue. Checking my mobile, I can see. Yeah. Okay. So let me continue. Uh, okay. So the percentage bias differential relay or bias differential relay or percentage differential relay. This is the most extensively used differential relay. Okay. Here also we can the relay coil that is used here. It can be an operating overcurrent relay. Okay, we can use and in the beginning I told you that any type of relay can be used as differential relay. So here we can use an overcurrent type of relay. Okay. Uh, if you just compare this diagram with your previous diagram, it is somewhat similar. So this is the element which is to be protected. It can be generator winding or transformer winding or any bus bar or transmission line which is to be protected. So the boundaries of the protection are decided by the location of the CTs. So at both ends of the element which is protected, CTs are connected, CT1 and CT2. And we know across the secondaries, what should be there? What should be there? Relay coil should be there. Okay, relay operating coil should be there. So along with the relay operating coil, there is another coil here that is restraining coil. So biased differential relay or percentage bias differential relay. This relay will have two coils. Okay, so one is operating coil. Where is my cursor? Yeah, one is operating coil. Another coil is restraining coil. Okay, so it has two coils, operating coil and restraining coil. Uh, and if you observe these two coils, this is our restraining coil, this is our operating coil. I will erase them once again. So this is our restraining coil, this is our operating coil. And if you carefully observe here, this operating coil is connected to the midpoint of the restraining coil. Okay, operating coil is connected to the midpoint of the restraining coil. So the reason for using this sort of modification is circulating in this differential biased relay is to overcome the trouble that is arising out of difference in the CT ratios. So if this sort of arrangement is used and if there is any difference in the CT ratios, that can be overcome by this sort of arrangement. Okay. So the difficulties which I have discussed earlier, those difficulties can be overcome by using this sort of arrangement. Okay. Now if you observe here, these two coils, restraining coil and this operating coil, they are wounded across two limbs. Okay. So I can say this is an electromagnet. This is an electromagnet. Two electromagnets are here. So let's assume the operating coil turns, number of turns are N naught. Okay. So restraining coil number of turns are N. Number of turns in the restraining coil are N, and the number of turns in the operating coil is N naught. Okay. So as this operating coil is connected to the midpoint of the restraining coil, the number of turns of the restraining coil are divided into N by 2 and N by 2. Okay, so the number of turns are divided into two portions, that is N by 2 and N by 2, whereas number of turns of the operating coil is N. So now, and if you see there is center hinge here, can't say hinge or center support, we can say. On this, with the help of, on this center support there is a beam, and there is a counterweight here. This triangle is nothing but a counterweight which is holding this beam in position, and this is our moving contact. Okay, MC, I will write MC, moving contact, and these two dots are our fixed contacts of what? Of trip circuit. Fixed contacts and moving contacts. So you can see here it is mentioned trip circuit. Okay, so we already know the trip circuit should be under open condition. Under normal operating condition, if fault occurs, then only the trip circuit should close. Okay. So under normal operating condition, through load condition, the torque developed by the restraining coil will be greater than the operating coil. Okay. So under normal operating condition, current will not flow through the operating coil. Okay. Okay, normal current will flow through the restraining coil. So the torque developed by this restraining coil will be greater than the operating coil torque. So means if torque developed by the restraining coil is tau r will be greater than torque developed by the operating coil, tau naught. Tau r will be greater than tau naught. As I said, my cursor is not is very sensitive. So torque developed by the restraining coil, let us assume tau r. It will be always under normal operating condition, not always. It will be greater than the torque developed by the operating coil. Okay, that is under normal operating condition. So since it is greater than the restraining torque is greater than operating torque, so this moving contact will not come in contact with the fixed contact. In this diagram, it seems as if moving contact is in contact with the fixed contact, but it will be pulled back. Of course, there is a counterweight to avoid the moving contact to come in contact with the fixed contact. So now, if any internal fault occurs, okay, some fault has occurred here. Let us assume some fault has occurred. Okay, some fault has occurred here. Some internal fault occurs. Then what will happen is the current flowing through the operating coil will become greater than current flowing through this coil will become greater than the current flowing through the restraining coil. Okay. So the torque developed by this developed in this operating coil will become what will happen? It will become greater than the torque developed in the restraining coil, that is tau r. So tau naught will become greater than tau r. So when the operating coil torque is greater than the restraining coil torque, what will happen is this moving contact is attracted towards the fixed contact and trip circuit is closed. When trip circuit is closed, what will happen is trip coil is when trip circuit is closed, yeah, trip coil is energized and circuit breaker is open. Okay. So now uh, this diagram is the schematic arrangement. Same diagram which is shown here. It is the equivalent circuit of the above diagram. Okay. This is the equivalent diagram, you can say. So it is the equivalent circuit diagram of the above diagram. So this is our restraining coil, or you can even call it as biased coil. This is our operating coil. So current flowing through the operating coil, as we have already discussed in the previous class, that is a differential current that flows through the operating coil. Okay. So this operating coil is connected to the center point of your midpoint. We can say midpoint of the restraining coil. Okay. So the number of turns in the operating coil is N naught, and the number of turns in the restraining coil is N, which has been divided into two parts because of this midpoint connection of the operating coil. That is N by 2 and N by 2. Okay. So this is the equivalent circuit diagram of this percentage bias differential relay. So the current flowing to the operating coil, as I have already told you, this is the I1 minus I2, whereas average current will flow through the restraining coil. Due to this midpoint connection, what will happen is average current will flow through this restraining coil. So the current flowing through the restraining coil is I1 plus I2 by 2. Okay, current flowing through the restraining coil. Okay, and what about the current flowing through the differential coil or the operating coil? I can't say differential coil, it is the operating coil is I1 minus I2. Current flowing through the operating coil is I1 minus I2, whereas restraining coil is I1 plus I2 by 2. So the torque developed, if fault occurs, if torque is developed in the operating coil, the torque developed in the operating coil, okay, will be always proportional to the ampere turns of this okay, so it is proportional to the ampere turns. So torque developed is proportional to ampere turns. So tau naught is proportional to I1 minus I2. This is the current that flows to the operating coil. These are the number of turns of the operating coil. Okay. So the torque developed in the operating coil is tau naught will be proportional to I1 minus I2 into N naught. Similarly, the torque developed in the restraining coil, it is also proportional to the ampere turns. So tau R, it is also proportional to the ampere turns, tau r. So tau r is proportional to what? I1 plus I2 by 2 into n, number of turns of the restraining coil. So these are the top equations of this uh, percentage bias differential relay. So similar to the previous case of your current differential relay, here also, if any external fault occurs, then the relay will not operate. Okay, so if any internal fault occurs, then the differential current will flow through the operating coil and average current will flow through the restraining coil. This differential current will become greater than the average current, and hence the relay will operate. Okay. So the operating characteristics of this relay, except for the effect of control spring, that is counterweight at the lower currents, the ratio of the differential operating current to the average restraining current is always fixed. Okay, the ratio of what? The ratio of the differential operating current to the average restraining current is always fixed percentage. That's why, okay, that's why it is called as percentage differential relay. Okay, and we can even call it, as I already told you, biased differential relay, because the restraining coil is also called biased coil as it provides additional flux. Okay, so this restraining coil is providing additional flux, that's why we can even call it as biased differential relay. Okay, now let us see the, I think, characteristics. This is the characteristics of this relay. So if you see here, these characteristics are plotted for the average restraining current, that is the current flowing through the restraining coil and current flowing through the operating coil. Okay, so initially under normal operating condition, as I've already told you, there will be, so if you see here, this is the operating characteristics of percentage differential relay and differential current owing to CT unbalanced. This is the current that flows if CTs are unbalanced. So this is the overcurrent relay pickup value. So the relay will not operate until predetermined value is reached. Okay. So this is the predetermined value. Okay. Some magnitude of fault current that has to flow beyond if the current is means if it is less than this value. Okay. This current, if the current is less than this magnitude, some here we are not giving any number here. It depends on the equipment which is to be protected, its ratings. Okay, depending on rating of the equipment which is to be protected, relay operating current will change. So uh, until required amount of differential current flows through the relay will never operate. Okay. So this character, the first one which is showing here is operating characteristic of percentage gas differential relay. That is, as the restraining current in here, as restraining current is increasing, operating current is also almost increasing. Okay. Similarly, if the CTs are unbalanced CTs turns ratios are not same, so there is an error in CT turns ratio, then what will happen is, even under, means even though predetermined value, okay, fault current, operating current has not reached to the preset value, the relay may operate, okay, unnecessarily. Unnecessary relay will operate even under even though fault is fault is not a severe fault, or if CT turns ratios are not same. Okay, under such condition, actually relay should not operate below this uh, limit, which has been mentioned here. Okay, below this limit, if current is there, it means if the difference of I1 and I2 is less than this limit, then relay should not operate. Beyond it, it has to operate. Okay, so that limit is decided by the engineer. Okay, so depending on the equipment which has to be protected, depending on its rating, he will decide what should be the differential current beyond which. Okay, differential means operating current difference of I1 and I2. Okay, if it exceeds that value, then the relay should operate. But if CT turns ratio is unbalanced, then unnecessarily relay may operate. Okay, so this is I think I have to here. I will make certain arrange. So this is one type of relay, that is induction type biased differential relay. So percentage biased differential relay, it can be induction type biased differential relay. So let us discuss about this. So this is, if you carefully observe, it is looking like an electromagnetic induction type relay, isn't it? It is looking like somewhat as electromagnetic relay. Okay, so it has some what is it, limbs. Okay, it has some limbs. Along with one limb is split into two parts, isn't it? And to the split portion, what is that? To the split portion, one copper ring. Okay, shaded limb. Okay, we can call it as shaded limb. These are the shaded limbs. You can see here. So it's looking like an electromagnetic induction type relay. You can even see this black thick line. It is the movable disc. Okay, So this is induction type biased differential relay. It is the simplest electromagnetic relay, and this relay consists of what? A disk which is free to move. We will usually call it as pivoted disk. Okay, which is free to rotate in the air gap of two electromagnets. So how many electromagnets are there? This is one electromagnet. This is one electromagnet. Okay, two electromagnets are there. To this electromagnet, a coil is wounded. To this electromagnet, a coil is wounded. Okay, a coil is wounded to both the electromagnets, and this here, if you see, they have mentioned here something operating element. So means the current flowing through this coil is, okay, differential current. Okay, and here they have mentioned restraining elements. The current flowing through this coil is average current. Okay, so differential current will flow through this coil. Average current will flow through this coil. So we can say that this is operating coil. This is restraining coil. Okay, and you can see, if you carefully observe, this winding is connected to the midpoint of this winding. So definitely this is our restraining coil. The other coil is our operating coil. Okay. So here two electromagnets are there. So the disk which is pivoted disk which is available here, it will experience two torques. Okay. It will experience two torques, one due to the operating element, other due to the restraining element. Okay, if the shaded ring, which is shown here, the shaded rings, this is the shaded ring, this is a shaded ring. What is the need of shaded ring? I have already explained. Why shaded ring is provided, I have already explained. So this shaded rings were in the same position in each element. In all the limbs, they are located at the same location. If they are located in the same location, then the resultant torque experienced by the disk will be zero. Okay, if they are located at the same position, the resultant torque, which is explained by the disk, will be zero. But if the shaded rings of the restraining element were moved further into the iron core, they are moved further into the iron core means what? They are moved further up. This is up. This shaded ring is moved up. And this shaded ring is moved down. Okay, move towards the iron core means that's what, towards upper one, towards the, it is moved into the iron core. This is moved into the iron core. Then the torque exerted by the restraining element will exceed the torque exerted by the operating element. Okay, so if this shaded ring, this shaded ring, this shaded ring, and this shaded ring, they are at same location, the torque experienced by the disk will be zero. If the restraining torque are shaded rings, okay, these two rings, if they are moved into the iron core, then restraining torque will become greater than the operating torque. Okay, then and relay will not operate. Okay, then relay will not operate. Now if fault occurs, okay, so under no, that is under normal operation. If fault occurs, okay, so this is they are moved inside the iron core under normal operating condition, they are left. If fault occurs, even though they are these shaded rings of the restraining element are moved towards the iron core, the fault current is very severe. Okay, the fault current will cause the differential current to flow through this operating coil, and restraining current, whatever restraining current that is flowing through this, that is the average current that is flowing through the restraining coil. Okay, the differential current will be definitely greater than the restraining coil current, that is the average current, and that will cause the disk to rotate. Okay, so this is the operation of induction type percentage bias differential relay. Next, voltage balance differential relay. So in this voltage balance differential relay, you can see this is the element. Where is my cursor? Element that is to be predicted. Again, there are two CTs, CT1 and CT2, and I1 is the entering current, I2 is the leaving current if internal fault occurs. Okay, and E1 is the induced EMF across the secondary of the CT1. Okay, E1 is the induced EMF, and E2 is the induced EMF across the CT2. And you can see the relay coils are connected in series to the parallel wires. They are connected in series to the parallel wires. Okay. So usually current differential relay is not suitable for the production of feeders. Okay. So the in such cases, so protect the feeders, usually this type of voltage bias differential relays are used, especially to protect the feeders. So the voltage differential relay uses two similar current transformers. Of course, we know that CT should be always of same ratio. Okay. And the relays are connected in series with the secondaries of the CTs, current transformers. Okay, relay 1 and relay 2, which is shown in this diagram. They are connected in series to the CT1 and CT2. So these relays are connected in such a way that no current will flow through it in the normal operating condition. Okay, the relay 1 and relay 2 are connected in such a way that no current will flow through them under normal operating conditions. So the voltage biased differential relay uses the air core CTs. The CTs that are used here are air, AIR, air core CTs, in which induced voltages in the, okay, these CTs will induce voltages in the secondaries linearly with respect to the current. Okay, so means the EMFs that are induced across the secondaries will be linear to the current that is flowing through CT. Okay, that's what it is meant. It meant. Okay, so when the fault occurs on the protected zone, that is in within the protected zone, then the currents in the CTs will become unbalanced. Means current entering CT1 and CT2 are no longer same. That is, if current I1 enters CT1, I2 will leave the CT2. Okay. So when current entering and leaving is no longer same, the induced EMF, this diagram is under faulty condition, isn't it? This is a fault condition diagram. So the induced EMF across the secondaries, which is shown in this diagram, will no longer be same. That is, E1 is induced across CT1, E2 is induced across CT2. Okay. And because of this EMFs which are not same, the EMFs induced across the CT1 and CT2, that is E1 and E2 are no longer same. Therefore, they will cause circulating current to flow through these operating coils of relay 1 and relay 2. The relay will start operating, and when relay operates, we already know what will happen. Trip circuit is closed, and trip coil is energized, and circuit breaker is open. Okay, it's so here percentage biased diagram, percentage restraining coil, operating coil are not shown. Simply we have mentioned relay, two relays are mentioned here. So when current, if internal fault occurs, current entering and leaving CT1 and CT2 will no longer be same. Hence the EMF induced across the secondaries will no longer be same. This will cause circulating currents to flow through the pilot wires. Hence relays will operate under faulty condition. Okay. So this is about differential relays. So I wanted to discuss even static relays. So most of you did not join the class on time. So I couldn't complete. So it's already 9:10 here. So I will just give you the link of the Google form, and you people can fill it. And if possible, tomorrow I may take the class. If I start the session now, then I don't think it will be late. That's why I'll just write some questions and I'll just upload, give you the link. Wait for a minute. Have given you the link. If you have any issue, inform. If it asks you to ask permission, you just uh, just send me the email and I will give you permission. Is the Google form working? Just mention in the chat box. Are you able to fill it? Is there any issue? Let me check. Yeah, it's opening for me. I don't know about you. I will just try to. Yeah, it's opening for me. So fill the Google form. If you complete, just mention that you have filled the Google form. You just mention completed and you can leave the session. If you have filled the Google form, just mention in the chat box and you can leave the session. Is there any issue with the Google form? If there is an issue, just mention in the chat box. Completed? Okay. If no issue with the Google form, then it's okay. If you have completed, you can leave. Okay, then it's good. If there are no issues, then it's good. If you have completed, you can leave. No need to be in the session. I'm just waiting so that if anyone, for some people, they are the once again uploaded to Google Form. possible, tomorrow also I will take this session at the same time. To complete many topics. So I hope everyone have left. They are managing this stream.